So here's a few questions about some other properties of water that are very, very important, especially when we start talking about infiltration of water into soils. These questions include these, and this is just really an exploration of the surface tension effect of water. At what temperature is the surface tension effect the maximum? Another is at what temperature is the surface tension effect the minimum? And if we increase the temperature of water, what happens to the surface tension effect relative to the temperature that we started? Okay, so this helps answer a couple of those questions. Surface tension is a force, and it's expressed usually in newtons per meter, or kilogram meters per second squared per meter. And what this force does actually is that it's actually applied at the edge, the interface between, or the contact point between water and the substance that it's coming in contact with, and it's pulling water because of the hydrophobic bonds of the water molecule itself. It's pulling water, the skin of the water away, and actually helping to form a skin on the water. In this equation, temperature is in degrees centigrade. So you can see that if temperature is at 0 degrees centigrade, then the term on the right-hand side goes to 0, and our surface tension effect is the maximum. Now this would be for liquid water. And at the minimum surface tension effect would be just before water turns to vapor at the boiling point, which is when temperature is equal to 100 degrees centigrade. As you might guess then, the surface tension of pure water as a function of temperature, and remember, one of the things that's important to know about this graph is that it goes well beyond the bounds of temperature in which water is a liquid. It goes from 0 to past 350 degrees centigrade, something one could achieve if one had adequate pressure, but in most cases, the cases that we're all familiar with, our bounds are between 0 and 100 degrees for liquid water, or for water to be a liquid. And you can see though that the surface tension effect decreases as water warms within the range that it's a liquid. The surface tension effect is partly determined by the properties of the medium in which the water is coming in contact with, okay, and partly the chemical properties of the water itself. You can see at the top it's a diagram of how the surface tension effect is actually applied and what the vectors of forces look like. But the take-home message from this is just that the surface tension effect is applied at an angle so that it's drawing water upwards toward the skin of the water in a way that allows it to actually pull up volumes and masses of water based on the amount of force that's being applied by this surface tension effect. Different substances interact with water in different ways to alter the surface tension effect. If, for example, you look at the top drop, that might be very typical of water on a hydrophilic substance, which could be glass. The contact angle is very low, and what that means then essentially is that water might spread out over a glass surface and wet it entirely, rather than beating up as water might do on a leaf surface. If you look at the illustration below, the diagram of how water might look on a glass surface, you see water in a bead, almost a perfect sphere. And that's because the water molecules themselves are drawing together on a surface that is, say, a waxy leaf surface that actually repels water to such a point that we end up with a sphere rather than a film of water. This can work when the volumes of water and the masses of water are very, very small. In this case, again, like a drop of dew on a leaf surface. Now, one of the things that you can do that's really interesting is find a YouTube video of the Jesus lizard to see a demonstration of taking advantage of surface tension. If you get a good YouTube video and you look at it, one of the things that you'll be able to see is that the Jesus lizard's foot, a webbed foot, splashes down in the water, and the mass of the Jesus lizard itself is so small that it's able to almost seemingly stay afloat on the top of the water surface, even though you can see in the videos that it penetrates quite far. The Jesus lizard is actually able to move its feet quickly enough and high enough to continually take advantage of surface tension to run across the water surface. Capillary rise is an important surface tension effect. And here's an equation that demonstrates the height of how the height of capillary rise can be predicted. On the top we have the height, on the left hand side we have h, which is the height of capillary rise. On the right hand side we have 2 sigma, which is the surface tension effect, which is modified by the contact angle, which again is a property of the medium in which water is coming in contact, and that's divided by the density of water, rho, on the bottom, looks like a P, but it's a rho, times the force of gravity times the radius of our capillary. So what does this mean? Let's explore it a little bit for a minute. What this means on the bottom is that if the radius of our capillary increases, so it becomes very, very large, then the height of rise is going to decrease. So that's an important thing when you think about how water rises in a straw. If we put water in a straw, or if we put a straw in a glass of water, okay, we might see a rise above the surface of the water that's contained in the glass. Go further out, if we have a plastic glass, if we go to the edge of that glass, one of the things that we'll see is that the height of rise on the exterior of the glass is going to be smaller than the height of rise within the straw, and that's predicted in part by this equation because of the radius. The radius of the glass is much larger than the radius of the straw. A couple of other things. The modulus of expansion of water is important as well. As we've already pointed out, density varies with temperature. When we go, however, from a liquid to a solid, the volume expands by 9%. It increases by 9% upon freezing. You can demonstrate this for yourself by putting a bottle of Coca-Cola in the freezer. When it freezes, the volume will have expanded by 9%, and it will break your bottle. So, if the temperature changed from that, so to illustrate that, thought question, if the temperature changed from 4 degrees centigrade plus or minus 4 degrees centigrade, and we had a completely filled container, how would the volume change? Well, obviously, if the temperature drops to the freezing point and we have solidifying of the water inside, this represents the case in which the volume is going to expand by 9% and likely break the bottle. But if we go up 4 degrees centigrade, our volume will change very little because the density varies very, very little with the change in temperature. Modulus of compression is important, and that's in part because water is relatively incompressible. 1 pound per square inch of pressure can decrease volume by about 3.4 times 10 to the minus 4th percent, so very, very little. So a pressure of 100 pounds per square inch, about the pressure that we have in a nice racing bicycle, would decrease volume by far less than 1%. So it's relatively incompressible. Pressure really matters very little in terms of determining the volume of water. And here's what this means: that water is pretty efficient at transferring kinetic energy when it's enclosed in a rigid structure. So for example, if we put it in a pipe and we put a plunger in the pipe and force and put pressure on the water, rather than compressing is going to have to move to another part of the pipe rather than be compressed and actually occupy a smaller volume. So if we can harness that in all kinds of mechanical devices to take advantage of the fact that it's a good way of transferring kinetic energy. Water is a great way to transfer energy of another sort, and this has to do with the global balance of energy. In a liquid phase, water absorbs about a calorie per temperature rise of 1 degree centigrade per cubic centimeter. The other thing that means, though, is that when we get to 100 degrees centigrade, we have to add an additional 539 calories to go from the liquid to the gas phase. Think of that as evaporation. And when we go from the liquid to the solid phase, we release 80 calories per centimeter cubed. So liquid water can not only absorb and store large amounts of energy, but as it changes phase, it absorbs even more. And this is very important when we start thinking about the global energy balance. When we think about the amount of water that comes from the sun and lands, is absorbed by the face of the earth, one of the ways that the energy is dispersed across the entire planet is by global cycles of climate that involve evaporation and condensation as large currents of air carry water from one part of the globe to another. In terms of other applications though, sweating is vaporization for cooling. Liquid water on a hot free surface requires 439 calories per cubic centimeter to become a vapor. The result is a substantial loss of thermal energy, which means cooling. And here's an example of that: car cooling systems. Flowing water efficiently transfers heat away from hot spots created by friction.